So this problem is about the Laplace transform of some simple functions basically L of t, the Laplace of t, the Laplace of t squared, and in general Laplace of Tn for n equals 3, 4, etc. So instead of doing Laplace of t and Laplace of t squared, let us try to see what is Laplace of t n plus 1. So here we take n greater or equal to 0, and we look at the Laplace of tn plus 1 at s. So this is by definition the integral from 0 to plus infinity e minus st t to the power n plus 1 dt. So here we are looking at, since n is greater or equal than 0, so there is no problem, no other bad point except plus infinity. And in plus infinity, we can easily prove that if s is less or equal than 0, then we are divergent. So if s is less or equal than 0, we have divergence. And if s is greater than 0, we have convergence. So the domain of the Laplace will be s greater than 0. And in order for us to, so we know, we know that from 0 to plus infinity e minus st t to the power n plus 1, because they are asking us to find Laplace. So let us use the definition of the improper 0 to a e minus st t to the power n plus 1 dt. So we are going to use the antiderivative. So here I have to find e minus st t to the power n plus 1 dt. And for that, we're going to do an integration by parts. So we're going to integrate uh, this one, and we are going to differentiate this one. So integration by parts. So we find this is minus 1 over s e minus st t to the power n plus 1, and then plus 1 over s, the integral of e minus st n plus 1 t to the power n dt. So this is equal minus 1 over s e minus st t to the power n plus 1 plus n plus 1 over s, the integral from 0, the integral of e minus st t to the power n dt. So here, if I go now from 0 to a and look at the limit, using the fact that the limit of e minus sa a to the power n plus 1 goes to 0, by using Hopital rule, for example, we get that the integral from 0 to plus infinity e minus st t to the power n plus 1 dt equal, this one here will give us 0 at 0, and at a it goes to 0. When it goes to infinity, it goes to 0. So we are going to be left with n plus 1 over s, the integral from 0 to infinity e minus st t to the power n dt. In other words, the Laplace of t to the power n plus 1 at s is equal to n plus 1 over s Laplace of t to the power n at s. Is the same here, same variable s, okay? So using the fact that Laplace of 1 is 1 over s for s greater than 0, we come up now with all of them. So for example, as they asked us, Laplace of t is going to be n equal 0. So it's 1 over s Laplace of 1, which gives me 1 over s times 1 over s, and that's 1 over s squared. Laplace of t squared is 2 over s Laplace of t, which gives me 2 over s, 1 over s squared. That's 2 over s cubed. Okay? And Laplace of t cubed is going to be 3 over s, Laplace of t squared, which gives me 3 over s times 2 over s cubed, 6 over s4. So by induction, one can easily show that this is n factorial s to the power n plus 1 for any n here, from any n 0, 1, 2, etc. Okay, so this gives me a formula for the monomial t to the power n. So from here, we can do now the Laplace of polynomial functions by linearity of the Laplace transform. Okay? So for example, if we take Laplace of t cubed minus 2t plus 5, we will find, so here we use the linearity of Laplace, so we have Laplace of t cubed minus 2t plus 5, that's Laplace of t cubed minus 2 Laplace of t plus 5 Laplace of 1. So that's the linearity of Laplace, or the basic properties, using the basic properties of Laplace. So this is 3 factorial, or 6 over s4, 2 over s squared, 5 over s, and one can reduce to the same denominator and come up with a general formula. So you can see now that if p of t is equal to a0, a1t, a2 t squared, etc., so polynomial function with degree n, then Laplace of p of t is going to be a0 over s, a1 Laplace of t, a2 2 over s cubed, etc., an n factorial s n plus 1.